Alrighty, hello everyone. I'm not 100% today, but I'm going to have a go through trying to finish up just chapter 3. I'll put the videos up so that you can watch them at your own speed, but you might be watching this all together just to start the day. Alrighty, so having a look at this one, we're just going to be looking at a 4x4 matrix. So the main thing this is going to change from when we were doing Hungarian algorithm in the last couple of lessons is that when we do the covering lines checks, when we're covering our zeros, in this case, because there are 4 people, we need to make sure that the fewest number of lines we need is 4. So because there are 4 people, we need 4 lines to cover the zeros. And if we don't get 4 lines, then we'll have to do that extra step. There's not a lot of space here, so we're probably going to have to write a little bit small. So I'm just going to copy down the table as a matrix to start off with. Alrighty, so I'm going to do my best to be as neat as possible. Alrighty, so step 1 in Hungarian algorithm, to minimize the cost, is going to be to do row reduction. Smallest number in the top row is 15. 15 for the second row. The third row is 16, smallest number. And the smallest row for the third one is also 15. And we can go through and do some subtraction. I'll do the first 2 rows, and then I'll leave it up to you. So 15 minus 15, 0. 16 minus 15, 1. 21 minus 15, 6. 16 minus 15, 1. Second row, 16 minus 15, 1. 20 minus 15, 5. 15 minus 15, 0. 25 minus 15, 10. Alrighty, I'll finish this one off camera. Alrighty, so I've finished up my row reduction, so I'm up to column reduction. Smallest number in the first column, 0. Smallest in the second column, 1. Smallest in the third, 0. Smallest in the last is also 1. So only the second and the fourth columns will actually change. The others will stay the same. So second column becomes 0, 4, 5, and 7. Third column stays the same. And last column becomes 0, 9, 5, and 1. Alrighty. So now we're up to the covering zeros check. And with this, sometimes, especially in a larger matrix, it's always going to be harder to cover your zeros. But again, the same principles apply, which is that you want to find a line that you can draw that's going to cover as many zeros as possible. So for example, this top row here, that covers 3 zeros just for one line. And then you can see, well, this one covers 2 zeros with one line. And so then the third line is this. But again, 3 lines does not equal 4 people, because there's 4 people in this problem. So that means we are going to have to do that extra step. Now, obviously, as you know, we have to do something with the intersections. So it does actually make a difference in terms of what happens to our intersections, right? This is a must, this is a must, and then I could have done this. Well, where you draw your lines is where you're going to do the algorithm. So if I do that, then I'm going to use the algorithm on that. It's really important that you do draw your lines. So we take the smallest uncovered number. Smallest uncovered number is the 1. So we're going to subtract 1 from the uncovered. And we're going to add 1 to the intersections. And in this case, we actually have 2 intersections. We have this 6 and we have this 3. So we're going to add it to 2 different places, and then we're going to subtract it off these 4, the uncovereds, plus these 2 who are also uncovered. Alrighty, so let's do that. So we get 0, 0, 7, 0, 0, 3, 8, 4, 0, 0 stays the same. 9 becomes an 8, 5 becomes a 4, the 3 becomes a 4 because we've added 1 to it, and the rest of the uncovered numbers stay the same. And what do we do next? Well, we once again check our lines. So I see a 3 for 1 in the top row, I see a 3 for 1 in the second one, and once again, I think we can cover all of the zeros with just 3 lines. So once again, 3 lines does not equal 4 people. So we have to repeat the step again. And this is the important part of the flowchart, is that we actually repeat this covering row steps until the number of lines equals the number of rows. It's really important. It is actually a loop, and we're going to continue playing with this loop. And I definitely think I'm going to run out of space. So apologies for that. But anyway, let's go through. So the smallest uncovered number is 1. So we're going to take 1 from the uncovereds. And then we're going to add 1 to the intersection. Important point to make. I'm using a highlighter for the purposes of teaching this. In an exam, when you're covering zeros, it is an expectation that you either circle, so just to sort of demo it, that you either circle like so, or you literally draw a line straight through it. Those are the two ways you should be covering your zeros. I have the luxury that I can use a highlighter, but that's mostly to make it easier to look at. In the end, it is an expectation that you do actually draw lines over the top. Alrighty, so let's continue. Alrighty, so you can see I've just made myself a bit more space. So once again, I'm going to go through and take 1 from the uncovered ones and then add 1 to the intersection. So that's what I'm going to be doing next. Let's follow along this one. So top left is actually an intersection, so I'm going to add 1. Now that's a 1. 0 stays the same. 7's going to get added, 1, 2, so it's an 8, 0. And the rest of the covered numbers are going to stay the same because they're not intersected. And then I'm just going to subtract 1 for all the uncovered ones. So 3 minus 1, 2, 3, 6. And then 7, 3, 0. And now once again, we're going to cover our zeros. This step continues until it succeeds. So I don't see any 3 for 1s, but I've got a 2 for 1 here, a 2 for 1 here, and a 2 for 1 there. But that still leaves me with the 0 in the corner, which means we're finally having to use 4 lines, which tells us that we're ready to allocate. So, draw the bipartite graph. Now we have to go back to the question just for a moment. It's Amanda, Borat, Chrissy, and Digby, so A, B, C, D. And it's an indoor spa, junior's bedroom, kitchen, and living room, so I, J, K, L. So, let's go through. A, B, C, D, I, J, K, L. And once again, we're going to draw that bipartite graph. So reading the top row, where we see zeros, that's going to tell us which jobs that person can do. So person A can't do job I, but they can do job J. Can't do job K, but they can do job L. Alrighty, let's have a look at person B. Well, person B can do job I and K, but can't do job J or L. Person C can only do job K. Do job K. And lucky last, person D can either do job L or job I. And there we get our bipartite graph. Now, to start off with, we've a little bit harder to allocate from here. The only easy one to allocate is actually C and J, because they only have one connector. So it tells us 2 of them. So C has to do K. C has to do K, and A has to do J. Since J is the only person who can do J is A. Alrighty. So what about B then? Well, B can't do K anymore, so B's going to have to do I. And then that just leaves D having to do L. And there is our allocation finished. So now we've got an allocation. Now we just need to work out the cost. So we can either go back to the original table, which is what I usually do. So CK, AJ. CK, AJ. And I think it was BI and DL, but let's just double check. Yep. So the total cost is going to be 16, 16, 16, 17. Now, it's a really important step now, just to make sure that we go back to the question and check what the numbers actually mean. So they're all designers. They quote the following: it costs in thousands of dollars. So this isn't actually $65. It's actually $65,000 is the minimum cost. Alrighty. So we've now had a look at that one. Alrighty. So there's a couple. This question here that you can have a crack at yourselves, and then I'm going to show you how to do 3.9, which is in a maximization problem using the Hungarian algorithm. Alrighty. So hopefully you've had a go at the other one. If not, you can pause the video and just, when you're ready, go through how to do 3.9, which is how to turn a minimization algorithm, which is what the Hungarian algorithm does. It tells us the minimum cost. What if we want to maximize something? So the basic idea is that what we want to do is for each number in this table, we want to make the biggest number the smallest number and the smallest number the biggest number. So we kind of want to invert it. We can sometimes call it a complementary matrix because in a sense it's kind of the complement to it. One says which cells are the biggest and which ones are the smallest. So what can we do? Well, we can actually do a bit of subtraction, and that will actually flip the whole thing. So let's take our biggest cell, for example, the number 25. If we go 25 and then subtract whatever the numbers in the cell is, well, the 25s are going to become zeros, and say the 15s, well, 25 minus 15 is 10, which is bigger than 25. So we can actually invert it by doing a sort of a funny operation, but we find the largest cell, and then we go that number, subtract whatever number is in the actual table. So that gives us this new table. So 25 minus 15 is 10. 25 minus 16 is 9. 25 minus 21 is 4, and so on and so forth. So I'll just finish that up. Alrighty. So now we've got an inverted matrix, right? The biggest numbers, which was 25 and 25, have now become zeros, and the smallest numbers, which were these 15s, have all become 10s. So you can see that basically it swapped the order. The biggest number is now the smallest, and the smallest is now the biggest. So we've now created the complementary matrix. Now what we do is we do Hungarian algorithm to minimize the opposite matrix, which is then going to tell us how to maximize the original matrix. A little bit of backwards thinking going on here, but let's just go through our Hungarian. So step 1 is going to be row reduction, and once again, really important. If you see a 0, that means that row is not going to change. So minus 4 for the top row, minus 0 for the second row, minus 0 for the third row, minus 2 for the next row, which gives us 6, 5, 0, 5, 9, 5, 10, 0, 0, 3, 9, 3, and for the bottom row, 8, 0, 5, 6. Alrighty, now we can do some column reduction. Minus 0, minus 0, minus 0, minus 0. Alrighty, so column reduction is going to change nothing. Alrighty, so we've now done column reduction. You can see nothing's changed. And now we can cover our zeros. So you'll see there's actually no 2 for 1s, which means that no matter which way you draw the lines, you will have to use 4 lines, which is exactly what we're looking for. 4 lines means ready for allocation. So let's just call the people A, B, C, D, even though there's actually no names, and I, J, K, L, just for the sake of it. And let's go through and allocate. So A, B, C, D, I, J, K, L. A can only do job K. B can only do job L. C can only do job I. And D can only do job J. And there we go. There's our allocation. A does K. B does L. C does I. D does J. Which then, if we go back to the original table, A, B, C, D, I, J, KL, you can see that the minimum cost, the maximum cost, because remember the whole point of this is to turn a minimum into a maximum problem, it's going to be 21, 25, 25, and 23. And there's our maximum cost. 21 plus 25 plus 25 plus 23, which is going to equal 94. Let me double check that. Yeah, 94. So that's actually the maximum. Alrighty, so that's how you can actually go through and do some maximizing. Alrighty, so you can see now we have actually finished chapter 3. And so hopefully for the rest of the lesson, you can just have a crack through some of these questions. They do get harder and harder. And as a reminder, there's review questions at the back. So if you finish all of these questions but still are feeling a little bit rusty, or not feeling 100% comfortable, or you're making lots of mistakes, please go back and practice some more. Lots of questions in the book. You don't have to do the same question twice, but if you are making mistakes, please go through them. Hopefully I'll be back on Friday, but otherwise, I'll see you next week. Adios. Bye.